Hi guys. I decided to make a video series about Tesla coil in which I will analyze, simulate and build different types of Tesla coil. In general, we have three types of Tesla coil. We have spark gap Tesla coil, vacuum tube Tesla coil and solid state Tesla coil. I will start this video series with building a spark gap Tesla coil because it has a very simple construction and everyone can easily build one. Later, we will build the other type of Tesla coil. Even though a spark gap Tesla coil has a very simple construction, but a properly designed spark gap Tesla coil can teach us a lot about different aspects of electrical engineering. The first aspect is about high voltage. So how to properly design the structure of the Tesla coil in order to avoid unwanted discharges. We don't want discharge on the surface of the secondary. We don't want discharge between the secondary and primary. We want to avoid all the sharp points inside the structure because we don't want the streamer to come from random places. All the issues that are related to high voltage. For example, what is the relation between the voltage of the top load and the length of the discharge? For how long time the gas will stay ionized when a streamer is propagated through it? So what is the relation between the repetition rate of the streamer and the length of the discharge? All these aspects that are related to high voltage, we will be able to learn if we have a properly designed spark gap Tesla coil. The second aspect is about interference and damages that these large discharges can cause to the nearby equipment. So how can we safely operate a Tesla coil without damaging our equipment? Maybe we can perform some measurement and calculate and measure the intensity of the signal versus the distance to the Tesla coil so that we have some guideline about the safe distances. The third topic, which is extremely important, is about resonance circuits. So how to measure and calculate inductances and capacitances. How to measure the resonance frequency of a circuit. How to tune this circuit, tune the primary circuit with the secondary circuit. What is the impact of the frequency on the value of the inductance, on the value of AC resistance of the coil? What is the impact of the resistance of this circuit, the coil resistance together with the spark gap resistance, on the total performance of the system? How does mutually coupled inductor work? What is the impact of the coupling factor? All these issues that are related to resonance circuits, we can understand by analyzing this spark gap Tesla coil properly. Now, these resonance circuits has application in many other areas. For example, if you are designing a wireless power transfer for your mobile phone to charge your mobile phone, or the bigger one to charge an electric car, these are very similar concepts. You have two coils which are basically coupled and they operate at certain resonance frequency and the energy is transferred. So if we understand the resonance circuit in Tesla coils, we can use this knowledge in other applications. The last point that is very important is about safety. So what is the safe distance that we have to keep when we operate this type of Tesla coil? Which part of the circuit is very dangerous and which part of the circuit maybe is not that dangerous? In general, what are the safety concerns that we have to follow when we operate a high voltage device? So this is basically the general background. Now, a few weeks ago, I have made my first spark gap Tesla coil, which I'm going to demonstrate it to you. And also I will tell you the story behind in which it triggered me to build this Tesla coil. I want to mention also one last point, because we are going to do very scientific work here together with excellent simulation, and obviously we will have experimental result. I'm thinking that there is a potential that we can write an article, maybe an open access article about this whole topic. So in that case, all the viewers who give constructive comments and help developing this article, they will be acknowledged in case I really realize this article. Okay, so now let me show you the Tesla coil and we'll tell you the story behind it. Alright, so here we have a typical circuitry to drive the spark gap Tesla coil. We have a power supply, we have the spark gap, the primary capacitance, primary coil, and this is the secondary coil. Now usually on top of the secondary coil we put a toroid to homogenize the electric field, and people call it top load. Now any coil has a self-capacitance. Actually, there are many capacitances inside each coil. Between any two turns, we have a capacitance. But let's say the main one, we call it the self-capacitance. And because we have a metallic object here, and this is the ground, so there would be also another capacitance between this top load and ground. So the self-capacitance of the coil together with capacitance of the top load will add together and would create this secondary capacitance. Now this secondary capacitance is a stray element. It's not a real component, but it's a stray capacitance. So the inductance of the secondary coil together with the stray capacitance of the secondary coil, this creates a resonance circuit. The task for us is to match the resonance frequency of the primary circuit, these two, with the secondary circuit. Now this power supply, it is a high voltage power supply. Usually it's 50 Hz, 60 Hz step-up transformer. Or you can actually use a weak DC high voltage power supply. To make a DC power supply, we can use a flyback transformer. Flyback transformers that are used in all TVs, they already have internally a rectifier, so we will get DC at the output. So the task for us is just to drive those flyback transformers to create this high voltage DC. In this video, I will use a flyback topology, which I will show you later. Basically, we have this power supply, so the voltage will be supplied here. Let's say at beginning the spark gap is open. So the current will flow through this loop, through this big loop. This primary inductor is only made of few turns, so it's almost short circuit. So the capacitance will start to charge. And you see that one side of capacitance is connected here. The other side is connected through this almost short circuit. So it's connected to the other side of the spark gap. When the voltage of capacitor reaches a certain value above the breakdown strength of this spark gap, basically here we will have a spark. So if there is a spark here, now we will have a loop in this smaller part. Basically, all the voltage of the capacitor will drop over this arc resistance together with this primary coil. So thousands of volts would drop over this circuitry. And so hundreds of amps, maybe thousands of amps would flow through this loop for a very brief moment of time, several microseconds. So a high current passing through this primary coil will create a magnetic field. This secondary coil is loosely coupled with the primary coil, so it also sees that change of magnetic field, and because it has many number of turns, a large voltage will be induced on the secondary coil. Now if the voltage is sufficiently high, the electric field here will be sufficiently high, and if it is higher than breakdown strength of air, it will basically ionize the gas and create a discharge. That is what we see in Tesla coils. Now every component of this circuit is extremely important. Spark gap, the power supply, the strength of the power supply, the type of the capacitor that we use here, the coupling between these two, and all the other details. These things we will cover in future video. This is just an introductory video, so I don't want to go too much in detail. Okay, so now let us look at different phases of construction of a simple spark gap Tesla coil.
So everything started a few weeks ago when I walked into my kitchen and I saw an empty salt container. Immediately I realized that I can put some wire on it and build a secondary coil of a Tesla coil. So I went on with it and built the secondary coil. In a minute I will show you how I made it. But I have a few points that I want to mention here. So this material is made of cardboard. Paper and cardboard can easily absorb moisture. So if you leave this one in an area where the moisture content of air is high, or by accident you pour some water on it, it absorbs moisture, and if a high voltage is created over this coil, the discharge can form through this cardboard and basically destroy your secondary coil. So in general, it is recommended to use a better material, for example plastic, as this support structure. Maybe a PVC pipe is a choice. So also you have to be careful that the material that you use doesn't have conductive particle. So for example, white PVC or maybe gray PVC, they are good choices. Another point that I want to mention is about the aspect ratio of the coil. Aspect ratio is the height of coil divided by the diameter of the coil. Usually it is recommended to have a number between 3 to 6. For a medium-sized coil, maybe the aspect ratio can be 4.5 or maybe 5. Now, the exact reason why this aspect ratio is important, I couldn't find it on the web, but probably it's because of high voltage performance or maybe coupling between primary and secondary. As soon as I find a reasonable explanation, I will share it with you guys. Now in my case, the aspect ratio is even less than 3, so I have deviated from the general guidelines. Sometimes if you are too much confident, you can deviate from the guidelines. But in many cases, if you are maybe stupid, you deviate from the general guidelines. Let's see what is the case for us. In order to make the secondary coil, I made this structure with a rod. The reel of wire goes there, and this one goes inside. So now the reel of wire can easily rotate. Now in order to put the wire over this tube, we can basically, you take always half a meter maybe of wire extra and then put a tape here, and then you can basically rotate this one to form the secondary coil. Now when we make the secondary coil, we want to have a constant tension over this wire. So in order to create that constant tension, in this situation it doesn't have. So at every moment it has different tension. So in order to create a constant tension, I did some innovation. I took a piece of a sponge and cut a little bit of it. So now if you place this piece of a sponge under this reel, when you drag the wire and you pull the wire, basically this reel will always feel a constant force on it, so there would be a tension on this wire. So in that case you can make a very nice and compact coil. So remember, when you wrap the coil, every half a centimeter or maybe 1 centimeter, use a piece of tape and place it on top of your coil, such that if you accidentally drop the coil, everything does not open. It opens only up to the point where you put the tape. Now in my case, I finished the coil and I realized that I didn't count the number of turns. So in order to count the number of turns, I took a high resolution image, and on computer I counted the number of turns, and it turns out to be approximately 740 turns. Now the wire that I use, this wire has 0.23 millimeter diameter. It's AWG 32. After I made the coil, I put a few layers of packaging tape on it. Packaging tape has excellent insulation properties, so hopefully it prevents damaging the secondary coil. So this is the final product, which I am going to show you now. It's not pretty because it has a lot of packaging tape on it, but it's okay. So the end of it, I stick it to the ground plate, and the top part of it, the top load is connected. Now this plate my mom gave me when I came abroad. She thought that maybe in the first few days I could not find any plate to eat food. So these stainless steel plates, they're going to last maybe another 100 years. So they are really good. Now in this case I use them as ground plate. Alright, so this is all for the secondary coil. To make the primary winding, I use the normal household wire. So we connect all the 3 wires together. So this would be one conductor. By dividing the conductor into 3 sections, we can reduce the AC resistance at high frequencies. Maybe that can contribute a little bit. So the primary winding can come in different shape. You can make a pancake coil or a cylinder or maybe a conical shape. If you want to make a conical shape for a small size coil, you can use these things. They are usually used for sport, I think. So then you can wrap the wire around it and use packaging tape to hold the wire together, and then you can remove it. So you will have a kind of conical shape primary coil. Now first coil that I made was this one, but I quickly found that a lot of sparks happen between the secondary and primary, because the diameter of the secondary is also very large, or almost a little bit distance was available. So there was a spark between the secondary and primary. So I decided to increase the diameter. And then I gave up the conical shape because I didn't have other structure to wrap it around. So then I use a yogurt container and I wrap the wire around this, and basically at the end put some packaging tape on it, and then when it's a bit solid you can remove it. This is the outcome. So this is the primary winding that I made. It has in total 1 turn, 2 turn, 3, 4, 5, 6, 7 turns. 7 turns, and also approximately 20 centimeters from each terminal. So all of the wires are connected together. And then this one will connect to the rest of the circuit. Okay, so far we have made the secondary coil, and also we have made the primary coil. Now usually the primary coil is made of bare conductor. Copper pipe is a popular choice to make the primary coil. The reason is when you want to tune the primary circuit to the secondary circuit, you want to be able to change the number of turns on the primary, because that gives you flexibility to tune the circuit. Now in this case we use the wire with insulation around it, so we do not have that option. So if you want to tune the primary circuit to the secondary circuit, we have to change the primary capacitance. Of course, changing the number of wires is much easier, it's cheaper, but in this case, let's say it was very easy to construct this primary winding, and tuning the capacitance will not be also very difficult. Okay, so now we can put the primary winding into the secondary winding. Now another important part of the Tesla coil is the top load. In this case I used the hollow stainless steel sphere. These are usually sold as garden decoration, and they are not very expensive. Maybe each of this size is €4, and you can buy actually different sizes. When they are bigger, obviously the price will be higher. Now a better choice than this sphere is to use a toroid. Now when we connect this sphere to this end of the wire here, of course both of these regions, they have the same potential. But so officially we should have very low electric field in this region, because here and here we have the same potential. But because here we have sharp point, and this other part, which is the equipotential, is a little bit away from here, so at these sharp points we will have a field enhancement, and basically the discharges can be initiated from this point. If the voltage goes very high, we will see discharges from these regions, and this is not good, because if we have many of these discharges, eventually the coil will be damaged. However, if we use a toroid, the toroid will stay like this, and it is equipotential, so it's a metal, everywhere would be same potential. So we see that here we have, for example, the high voltage, and all these regions we will have also the high voltage. So because these sharp points are now located at a concave angle, so the angle is like this, then and the surroundings, they have the same potential, so the electric field at those regions will not be very high, so we will not get discharges from these regions. But a well-made toroid actually costs some money. So this size toroid, maybe it costs €50, which I did not want to make my bank account very unhappy. Therefore I decided to use this sphere. I thought about making a toroid myself. That is one option. So you can take a piece of foam and stick it together like this, or tape it, and then you put aluminum tape surrounding it, then it will create a toroid. And you put some kind of metallic plate in the center, so you will have exactly a nice toroid. But even when you put aluminum tape, even you make it smooth, still there would be sharp edges and sharp corners which discharges can initiate. But that is one option which I will work on it, and maybe if I get something nice, then I will show you. But at this moment this sphere is okay, even though we know that we get some discharges from this edge. For the capacitor, I use these red capacitors. These are rated at 2000 volt each of them, and they are 100 nanofarad. So I connected 5 of them in series, so we will get in total 20 nanofarad, and the total rating will be approximately 10 kilovolt. Now these capacitors, the internal construction is in such a way that you cannot really overstress them. So above 2000 volts, maybe 2500, maybe 3000, then
they are going to break internally, so you cannot overstress them. In a separate video, I will show you the internal construction of these capacitors and compare it with some other capacitors, and we will see why they cannot handle really overstress. 100 of these capacitors you can buy from AliExpress for 30 euro. Another type of capacitor is this type. These are also red capacitors, but they have a little bit different structure. These are rated at 3000 volts and they are 8.2 nanofarad. Now these capacitors, they are really well made and they can actually handle even more than 3000 volts, so maybe 5 kilovolts. Of course, if you apply higher voltage than what is written here, you're going to shorten the lifetime, but for a quick test you can actually overstress them to maybe 5, even 6 kilovolts. But these capacitors are also more expensive, so 100 of them you have to pay approximately 50 euro in AliExpress. Another type of capacitor that you might be tempted to use is these blue capacitors. These are 20 kilovolts, 10 nanofarad. But these capacitors, basically, they are not suitable for this application. These are usually DC. These are DC capacitors. So for this application, we will have a lot of high frequency, high voltage pulses. So if we pass many of those pulses through these capacitors, then they will overheat and eventually burn. But in case you don't have any other capacitor and you only have this one and you want to try, be careful when you make them parallel. So for example, like this is normally what people do. Okay, so you connect these two terminals together, you connect those two terminals together, so everything seems to be okay. But actually it's not okay. Because this leg of the first capacitor is connected to this side. But the other capacitor leg, the other side, is also connected to this side of this capacitor. So basically this high voltage that we have between the terminal will also fall in between these two capacitors, which may cause breaking through this region. So if you want to make them parallel, at least create some distance between them. But in general, I do not recommend to use this blue capacitor. You're going to burn them. I have already burned. These two are already burned. Use the red capacitors. Either this one, better would be this one. Another very important part is the spark gap. So in this case, I use a stationary spark gap. Basically, I took a piece of cardboard, I created bent here, and then put some packaging tape on these sides. So now we have the structure, created two holes. So basically we can put the electrodes inside and this will form the spark gap. Now for the electrode, I used the tip of a plasma cutter and soldered wire to them. So you can buy these tips from AliExpress, I think 50 of them for 15 euro. They are made of copper and then inside they have some tungsten. Now designing and constructing spark gap is really important and it actually needs to be cooled down properly. Now in this case it is not cooled down. So if we apply large power through this Tesla coil, then this one will get hot and spark will stay there. So that is a modification which we can do it in other videos. But for this moment, this is okay. Now, one maybe extra thing about the capacitor that I should mention, I did not put the discharging resistors on these capacitors because I am very careful about them and I will discharge them before I leave them. So in case you are making them, you better put discharging resistors on these capacitors. Otherwise you can get very nasty shock if you touch them. For the power supply, I decided to build this very simple high voltage power supply. It's a weak power supply, but at beginning for us is a good choice. Now this is a flyback transformer. We have a simple oscillator circuit here. This primary side has a main winding which has 4 turns and then has a feedback winding which has 3 turns.
So the winding will wrap up to here, and then you take this point and then continue another 3 turns. Now this part, the midpoint, will be connected to positive side of the battery, and this part, the main winding, will go to the drain of the MOSFET. This is IR3205 MOSFET. You need to use a heat sink because it will heat a lot. So I use a tiny heat sink here. And the third terminal will connect to the gate of this MOSFET. Here I have 2 tiny resistors, each of them 330 ohms. So totally we have 165 ohm here. And the source of the MOSFET will be connected to the negative side of the battery. So I will use 6.6 volts battery. So 2 3.3 volts battery in series, and that will power this circuit. So obviously the high voltage source that we have here is very weak. So the frequency of discharges that we get on the Tesla coil will be not very high. But for the start, this is already good. In a separate video, I will analyze this circuit properly, and we will perform some simulation to see the impact of the parameters on the performance of the circuit. For example, the number of primary turns, the number of feedback turns, the gate resistance, the type of the MOSFET, the leakage inductances of the transformer. All the important parameters will be analyzed, and through simulation we can maybe find an optimum point for this circuitry. This is a very common and simple circuitry that people use to produce high voltages, and I really want to analyze it. So this is a separate video which will come in the future. For the power supply, I'm going to use these 2 batteries. They are 3.3 volt each, so totally we have 6.6 volts. Alright, so now we'll connect the circuitry together. So one side of the capacitor should be connected to one side of the primary coil. This is rather easy. Okay. Of course, we do not want them to touch each other. The other side of the capacitor is connected to one electrode of the spark gap, and also high voltage is connected to that. So this is also connected. The other side of the spark gap will be connected to the other side of the primary coil. This comes here. Recently, life became very simple. Okay, so we have now spark gap is mounted properly, and obviously the other side of the spark gap also should be connected to the ground of the power supply. So that is this wire. Okay, so we have basically connected the circuitry. Now for the power source, as I said, one side, this one will be connected to the negative terminal of the battery, and this side will be connected to the positive terminal of the battery, and then we will have the discharges. So I will connect the negative side, but for the positive side I will make the room a bit dark, because then the discharges will start. Okay, so now I'm going to connect the positive terminal. In this case, I put the primary coil a little bit close to the secondary coil. And what you observe is that we probably will get discharge from the secondary coil to the primary coil. Obviously, this is not what we want, because those discharges are not useful, and if we have really powerful source, those discharges become so strong that it will burn the secondary coil. So certainly we have to put this secondary coil in the center. Now, because here I do not have discharging resistor for this capacitor, you have to always discharge this spark gap. So here I discharge. And now I put this coil like in the center. Okay, so now let us look at the discharges again. But you may notice on the back side still we have discharges to the primary coil. So now what I'm going to do, I'm going to lift the secondary coil a bit higher, because the voltage is built from the lower part up to the top part. So at these regions we have rather high voltage, and that is the reason why we get spark. So I use this piece of sponge and basically lift the secondary coil. So in that case, the voltage that is created in these sections will not be sufficiently high to create the discharges. So now we are going to avoid the discharges to the primary, hopefully. Stay in the center. Of course, the discharges are not very strong because we have some light in this room, so you will not be able to see them properly, but now I increase the gap distance a bit, and hopefully the discharges will be more visible. If you pay very close attention, you can see that there are some discharges also from these regions, which is really not desired. And the repetition rate of discharge is very low because the power source is very weak. If you would have a stronger power source, basically these discharges would happen more frequent and the ionized air will stay in place, so the next discharge could use that channel and actually propagate to a larger distance. Alright, so now maybe I will connect this one to a powerful source, and then we can see what happens to the output discharges. Oh, before I connect it to a powerful source, I realized that I have to do some experiments. These are very popular experiments that people do when they have a Tesla coil. So the first one is to turn on a fluorescent light. Maybe I can try. I'm not sure whether it works or not. Oh. Of course it creates. And I have also another light bulb. This one is a low pressure sodium light. So I did my duty and demonstrated these. I also have another light bulb. Maybe I can show that. Just a moment. This is a big one. I don't know whether this one will work or not. Ooh. Oh, yes. So this is also demonstrated. Okay, so everything is okay. Maybe I can also absorb some electric shock. This is a bit painful. Something is not working. Let me check. The negative terminal of the battery was separated. Everything is loose, so that's why it can create some trouble. Ooh. Oh. Oh. You can also notice the handle of the screwdriver, so the discharge will come and jump into my hand from there. Oh, this is painful. Wow. Alright. Alright, so that is sufficient. Now, as the closure of this video, we'll connect this Tesla coil to a bit more powerful source, and hopefully we'll get longer discharges. And then I will stop the video at that point. It doesn't work. So unfortunately the power supply will switch off as soon as the large discharges happen on this coil. So I need to select a better power supply. My power supply is a switching power supply, and this is not suitable when you use it with a Tesla coil because the disturbances will switch off your power supply.